In a fire station in Livermore, California, a single incandescent light bulb has been burning almost continuously since 1901. It is a testament to the capabilities of early electrical engineering. It proves a fundamental, uncomfortable truth. We have always known how to build machines that last for a century. Yet today, our most advanced hardware, smartphones, appliances, and vehicles, routinely fail or become obsolete within a few years. This degradation in durability isn't a loss of technological capability. It is a deliberate shift in industrial design. Welcome to the Cobra Paradox. Today, we're looking at the ultimate inversion of engineering principles. How industry shifted from optimizing for longevity to mathematically calculating the exact moment a product should fail. The paradigm shift can be traced back to 1924 with the formation of the Phoebus Cartel. Major light bulb manufacturers gathered in Geneva with a specific economic objective: revenue velocity. If a light bulb lasts forever, the consumer only buys it once. To sustain an infinite consumption loop, they needed to mandate finite product life. The cartel standardized a strict 1,000-hour lifespan for incandescent bulbs. From an engineering standpoint, this required actively reversing durability. Scientists were tasked with designing thinner filaments and altering gas mixtures to ensure the product would reliably fail at the target threshold. This was not a technical limitation. It was a mathematical target. Manufacturers whose bulbs lasted longer than 1,000 hours were financially penalized by the cartel. This concept, planned obsolescence, fundamentally rewrote the rules of manufacturing. Engineers were no longer solely tasked with making products better. They were tasked with making them ephemeral. Modern industrial design has perfected this system. Through the use of proprietary screws, glued-in lithium-ion batteries, and software locks, hardware is increasingly designed to be mathematically unrepairable. In economic terms, it is a highly efficient model for generating recurring capital. But geographically and ecologically, it creates a massive systemic imbalance. We engineered an economic engine that demands an infinite cycle of raw material extraction and disposal, operating on a planet with strictly finite resources. The model only works if extraction accelerates faster than depletion becomes visible. By intentionally designing hardware with an artificial expiration date, we transitioned from a product-based economy to a replacement cycle economy, contributing to a compounding global e-waste crisis. The physical limits of this consumption loop are becoming undeniable. Consequently, a radical pushback is emerging through the right to repair movement and new legislative frameworks. Regulatory bodies, particularly in the European Union, are beginning to mandate structural modularity. They are forcing manufacturers to adopt universal standards, like USB-C, and requiring consumer-accessible batteries. The new engineering mandate is attempting to legally force the industry back to its original objective: sustainable longevity. Whether it's minerals, concrete, or silicon, the pattern repeats. The obsolescence paradox teaches us a brutal lesson. When we optimize a system strictly for rapid consumption rather than sustainable value, we engineer our own resource depletion. And our optimization errors aren't just mechanical. Next time, we're looking at medical engineering. How our discovery of antibiotics, the ultimate weapon to eradicate bacteria, inadvertently forced the evolution of unstoppable superbugs. Every week, engineering analysis, pattern recognition, uncomfortable truths. Subscribe if you want to understand the systems shaping the modern world. This is the Cobra Paradox.